Greetings from Canada. My name is Emmanuel Odunlade. I'm an hardware design engineer and a chapter manager at a subsidiary of Hitachi, and also a solutions architect. And I probably spend more time than I should be writing blog posts and open source articles and stuff like that. And today I'll be talking about something that's very important to me. It's important, that's been an important part of my work, but also considering the current technology landscape and the speed of execution, something that's also very important to the way we develop hardware. And it's essentially how do we design the hardware design process in a way that reduces or eliminates the complexities and the lack of predictability and all of the issues that are associated with developing hardware devices. So in line with this for today, I'll be sharing some system architecture tools, system design tools that I have come to love and I found very useful for optimizing how you design, optimizing how you build hardware products. Now, at the end of this talk, I'm hoping I would have piqued your interest in these tools and also stir up your thoughts, get you thinking about how do we build hardware in a more efficient way. So some of the tools I'll be sharing today are things that won't be new for most of us. They're tools that if you work in industries that are very complex, like aerospace, automotive, these tools are probably used in decomposing systems, in early stage planning of product development. But then the interesting thing is that in some of those industries, I work in one of them, while you use those tools for breaking down these complex systems into modules and whatnot, we tend to ignore those tools when it comes to actually doing the design implementation. In another vein, in some companies and processes and whatnot, you have these tools spelled out as part of the development process and whatever that everybody follows to build those products. But then the tools are too complex. They are bulky because they are all wide designations for how you use those tools. It's the silent features of those tools that suits the mechanical team, but then they are an headache for the electrical team. So teams technically tend to just jettison those tools and fail to benefit from the values that those tools bring. And then in the startup, individual engineer, I'm building a product to sell on crowd supply kind of scene. We're all trying to fail fast, fail forward, and sometimes these tools tend to look like they're complex, they're bulky, you don't want to use them, you want to move fast and stuff like that, and then you end up missing some of the benefits and advantages that using those tools could have brought to your product development process. Now, every time I talk to someone about hardware development, either we're doing the post-mortem and kind of like evaluating how the process of developing a product went, we all try to kind of like chunk it to the fact that hardware is hard and and just blame and just put everything in that box. But a lot of times, some of the challenges that we face during the hardware development are because of missed unstructured decisions, missed trade-offs, and unexamined alternatives. One of the talks, and I promise I made the slides before the talk we had yesterday from Susan about batteries, for those that were here. And one of the major challenges of hardware development is missed trade-off analysis. We'll pick, because we're familiar with using a particular tool. I'm used to using STM for building this particular product, and this is not about STM, I'm just using it as an example. Familiar with using STM about this product, and even though I know that the the drivers or whatnot are not readily available, I'm going to tell myself, well, it's going to take my team is going to put the drivers together in 3 weeks. We're more familiar with this MCU, so we use it for that design project. And then 3 weeks down the line, the team is failing to deliver on those drivers, and that 3 weeks becomes 2 months. And at the end of the 2 months, we're happy, the product is in the market and all that. But if I had just spent maybe 2 more weeks to examine what are the alternatives, put it in a structured way to choose the best microcontroller for the project, I probably would have reduced that 2 months to just 2 weeks, and maybe pick something from Nordic or from just a random example. I mean, there's certain situations where it makes sense to stick with the microcontrollers that you're familiar with. But essentially, those missed trade-offs are probably one of the biggest reasons where our product tends to spin out of control and we run out of the timeline and whatnot. So everyone's favorite hardware problem, change propagation. And one of the reasons why these tools that I'm going to share today are important, especially for change propagation, is because the complexities of the products that we build these days are different. Now your chair needs a cloud engineer. Your toaster needs a software developer on the team. The products we're building are becoming more complex. The products, the amount of people involved in those products is becoming more multidisciplinary. It's becoming large. There are tendencies for the decisions made during the design process to be more based on opinions rather than data, because now you have too many people with biases, with preferences for how things are done, and we're all trying to pitch in into how that product is done, and those things affect how your product gets built. And sometimes we don't think about it, we don't see those things causing the problems, but when you step back and analyze your design process for the product, at the end of the day, you see how the opinions and aligning your team around opinions rather than data sort of affected that development process. So some of the tools I'm going to be sharing today are going to be focused around change propagation. I'll be sharing one tool that is useful before you begin the design process, one tool that is useful during the design process, and one tool that ensures you stay happy after the design process. Design structure matrix is one of those tools useful during the design process. And these tools are useful across board, not just for those specific examples that I've listed. But I'll be talking about design structure matrix. I'll be talking about weighted decision matrix and trade-off studies. And I'll be talking about sensitivity analysis. So what is DSM? So the product manager, they've done all of these analyses to determine what the features that needed to be built, and the order in which those features should be built, and then they send it to the engineering team, and or they put it in the backlog. And then the engineering team just, instead of actually doing the backlog analysis where you sort of examine how do these features interact, how do these features depend on one another, we just pick one of those features and then you start building. And then you're changing the enclosure, and then a few weeks down the line, just like we learned from the talk yesterday, a new regulation hits on the battery, and now, even though you've changed the enclosure, you now need a battery that, even if the enclosure gets shattered into pieces, the battery has to stay intact. I don't know if some of us were around for the talk yesterday about batteries. So essentially, DSM allows you to put together a list. It's an n-by-n matrix, and is based on the number of elements, the tasks, the features, the activities, everything you need to do in your design process. It allows you to kind of like map out the dependencies between each of those tasks. So I need to improve the speed of my design. I write it down. I need to improve my battery, my power supply. I need to do X. I need to do Y. I need to do Z. So you provide all of those on the horizontal, and then you have them on the vertical also. And then you start, and then you start mapping out those system elements and the interactions between them. So changing the battery has to do with, it's going to affect A, B, C, D. Now, this is something we tend to do, for most of us, but we do it in an unstructured way. we do it in a way that leads to, if you've ever held meetings with multiple engineers, we're technically egocentric. Our ego sometimes clouds our decision making, and then, but this tool allows you to kind of like get people talking about, those key design drivers, allows you to front load them and have those conversations early in a way that is structured. All we're doing, folks, is just marking out, this is gonna impact this, and so that we can sort of structure, what do we do fast? Essentially, that's the goal of DSM. What do you do fast? You wanna avoid cyclic change. You wanna avoid, omitting things that, that could lead to rework later during your design process. So, it allows you to map out systems elements and then interactions. This is blocking some of the things I have there, but it helps me break down complexity and sometimes shows some of the missed architectural elements of your project. So why DSM? It helps you optimize design sequence. It helps you spell out what needs to be done fast. Helps you make sure you're doing the right thing fast so you don't avoid cyclic change. Essentially, because of the kind of technology landscape that we are now, there's no time to horse around. You want to build, because by the time you try to do the rework to release the products in the market, there's someone else in the market with a product that is doing better than yours. So essentially, it helps you streamline the development process, reduce unnecessary iterations, and make informed decisions about what you're building. So out of DSM, it's like some of those tools. My goal today was to share like the streamlined version of streamlined way of using these tools. Some of them have heavy, for those of us that are in industry that complexity is inherent. Some of them have heavy applications, and you could spend days doing computing and all of that. But essentially, the way to use DSM is basically, write down the things that you need to do, the tasks, the features, everything. Have them on the vertical, have those things on the horizontal, and then use X to start plotting out how they interact. Now, there's certain scenarios where people do, where it goes more than that, where instead of writing X, you're writing the level of dependency. So for example, let's say your dependency ranges from 1 to 5. So instead of your processing speed, instead of just putting an X between your processing speed and your power supply, you're putting like a 5 to represent the level of dependency that those two items have on each other. So a quick example is something related to what we did yesterday. We say we have a product, and we want to increase the processing speed. We want to broaden the frequency range, and we want to redesign the power system for a new battery standard. I promise this was written before the battery conversation yesterday, because I know that also talked about battery standards. So this is really cutting the slides in the middle, and is there something I can do? Okay, there you go. All right. So what we've simply done here is that you black out the middle, because definitely it will interact with itself, right? And then you ask yourself, does increasing my processing speed, and this is done with a team. You do it with people that know about what is being built, right? You have your wireless guy, you have the firmware guy or whatever. So essentially mark out the interactions between the various elements, and then the two things you could do from here, and maybe I can go back to one of the previous slides. So one of the things you could do is that just based on these, you could tell that the power system has more downstream change impact on every of the other systems. So maybe it makes sense to at least keep all of the other systems in mind when you're doing any change in the power system. And also, so maybe the next thing to do after that is either the wireless processing, just because So the reason for that is because we have 4 axes in the power system on the change propagation part. So it means that you have more dependencies. The power system is going to impact whatever change you make to the power system is going to impact more elements in your system. So the next one maybe makes sense to say is the wireless support or the processing, but essentially this helps you see what directions your change could spiral in. Now, you could stop here, depending on if this was clear enough for what you need to build. But other things that could happen after this is sorting. You could decide to either sort or you could decide to cluster. Now, why is that important? An example of sorting is sorting allows you to see changes that can be done together. So sometimes it makes sense to do changes in the sequence. You do one first and then you do the next one. So, but sometimes it makes sense to just do certain changes together. It's probably cheaper, it's faster for your design team, and there's probably more business value when it's done together. But sometimes also there needs to be a sequence. So sorting allows you to see what are the changes that should be done together, what are the changes that should be done separately. And there, several algorithms for sorting. I think I mentioned that one in the free side that is like a word method for sorting. You could do more technical thing like partitioning around medroids. There are different ways to kind of do this sorting. Sometimes it's just using common sense to group items that are really dependent on each other into a box and say it makes sense to treat these items together and whatnot. Now, clustering is very interesting for me because of So sorting is very interesting because it allows you to do certain things after you've done the sorting. And one of those things is, so let's assume we sorted our DSM into 3 clusters. We have clusters A, B, C, and all of them are tightly dependent on each other, and we need to decide which of these clusters do we actually do first. Because essentially what we did with DSM was just group things that are dependent on each other, but now we need to decide, based on different factors, we need to decide which of them should we do first, which provides either the best business value to our customers, which provide either the best business value to our team, which of these clusters should be done first. And that is why things like weighted decision matrix are very useful. Now, I always tell people that this is a tool that fits even your own life decisions when you need to make decisions about life. It's actually a very interesting tool to use to kind of like write out what are the criteria for this decision that you're making, and leverage your team's technical capacity to write what are the things that should actually be the key driver for this decision. Assign weights to them. Usually, when you want to keep the weights, sum up to 100% or 1. Assign weights to those criteria, and then score each of those items, each of those decisions, each of those options based on the criteria that based on those criteria. And for example, say we have 2 options just from. Let's say we have 2 clusters, clusters A, cluster B, and you apply, and we've add weight. We say cost as 30%. 30% level of importance for what we're building, power as 20%, reliability, and things like that. And then the cost impact for option A is 8. And then you multiply it by the percentage of the percentage of the weight, and then that gives us. And so that just provides an easy way for you to do trade-off analysis, for you to compare 2 options in a very easy, very fast way to decide what to do first. And this is not just for sorting clusters. This could be useful for when you're selecting the microcontrollers. You create criteria, performance, power, whatnot, assign weights to how they're important, and then use these to kind of like sort through all of this. So I feel like I like to tell people that this is very important for whatever you do. So this is an example. This is another case. I mean, for those of us that have, maybe you're selling something on crowd supply, or you're running a small startup, or things like that. One of the things that's important when you are assessing features to be built is that you want to build features that align especially when you have a small team, you don't have time to ask around. You want to ensure that the features that you're building deliver the most impact, either for your business goals or your customer goals and things like that. And that's why I presented this example for a business that, revenue, whatever feature they want to build, they want to ensure that revenue has, maybe like 25% impact, cost reductions about 15%, risk mitigation. For example, you've launched a product into the market and you're worried that maybe the battery might go off or something about the design is wrong and you want to mitigate the risk early to prevent recall or something like that. So essentially you have this layout of your value dimensions, your business value dimensions, and then you go through, why is this? So, and then you kind of like, based on all of these dimensions, you score each of your clusters, based on these dimensions and say, okay, this takes this value, this takes this value. Now, one value that might be tricky there is the DSM elements there. And usually people call it it goes by different name depending on, some call it DSM centrality factor, some call it criticality factor, but essentially it just represents how dependent the elements in each cluster on each other. So some clusters might be tightly dependent on each other, and you want to do them because it's also dependent on the clusters around it, and some clusters might just be moderately dependent on other clusters around it. So you want to factor that into, and then one other item that you probably want to factor into this sort of analysis for business value or is the effort. So how much is this, to calculate what the business value is at the end of the day? How much effort is this going to take us to deliver this feature? How much effort is it going to take us to solve this particular problem in this cluster or things like that? So I found, weighted decision matrix very useful. You can apply it across every aspect of hardware development that requires you to make a decision. So now that you've made that decision, what happens when your value dimension changes? What happens when the elements that make up those criteria that you've listed, what happens when they change? For example, what happens when the tariff goes up? Well, that's still be the best country to do your manufacturing in, things like that. And that is where sensitivity analysis comes in. It essentially helps you evaluate what, so you've made a decision based on your weighted decision matrix, you've sorted through the clusters, you picked one of the options based on your weighted decision matrix, and now you want to just vary the importance of each of the weight that you assign to each of the factors or each of the criteria that you created initially, and you want to see how that impacts the decisions that you've made. So, for example, if the business goals go from more of risk mitigation because we feel like we need to ensure that our product is more stable in the market, so we want to mitigate that risk of recall. How does that affect, is cluster A or B or C or D is still the best design path for us to follow at this point in time? And that's where sensitivity analysis becomes useful. So essentially, it's holding one of these criteria in place and then varying the other. So for example, I think we changed 10 from 10, we increased customer uptake to 40%, and then we reduced cost reduction and risk mitigation. So play around with the numbers and see how it affects that decision that you've made, so that that just to make your decision making more robust. So now DSM is a very advanced tool. What I've shared today is just like a basic implementation that is possible within 30 minutes. It's a very advanced tool. It's used in aerospace, it's used in, it's heavily involved in research. I'm not a member of DSMweb.org, but I found it still very useful and I thought to share it today. But there are a lot of resources about how to use DSM at DSMweb.org. And yeah, it's a very short website, so it actually does not need the QR code. So the point today is that some of the things we chalk to hardware is hard are actually things that maybe we could design around. There are things that maybe we could leverage certain process optimization techniques to improve or make the outcome more reliable. And I think that's the core point of my pitch today. So for example, yesterday she shared about the battery, and what I was thinking was that, and she provided that chart, which was great to show, each batteries and their requirements, their whatever, and even their certification requirements. And, if after seeing that chart, you still made a decision to go with a coin cell, then maybe whatever happens after is not because hardware is hard. It was just because you made the wrong decision. So essentially, for us to go from the hardware is hard and firefighting, struggling to release products, we need to leverage tools that allows us to do some level of foresight. Leverage the systems engineering tools that are generically designed to actually break down complexities and bring them more into our design process. And lastly, so a lot of people call me the spreadsheet guy because I want to put every option into a spreadsheet and run it against data and come to a decision that is data driven. And like I say, in God we trust. All else must bring data. So it's not enough because we have biases in terms of, oh, I'm used to this tool. I've spent 10 years using this tool, and that does not mean it's the best tool for that job. We tend to bring all those biases into, and when you're dealing with well-trained engineers, everybody wants that opinion, and the best way to bring the team together is usually to just organize them around the data and rather than opinion. And yeah, that's my talk. Thank you. I'm always very interested in talking about those things because I think it makes our development process better. I feel like it makes hardware development simpler. I feel like it makes hardware easy to do. So, please reach out if you'd like to talk about it. I don't know if anyone else has any questions. I'm sorry that was it was a 20-minute talk, so I had to just compress everything into that. But yeah, thank you all for listening. If you have questions, please feel free to reach out and let me know. Thank you so much.